So now that we know a little bit about what an ideal gas is, we need to talk about something called gas stoichiometry. So we know our ideal gas equation, PV equals nRT or Puvnert, and we know that R is our constant and it's 0.0821 liter atmospheres per Kelvin mole. We can use this equation to convert between any of these different variables in moles to answer different questions related to a gas. So we can figure out the pressure or the volume of a certain gas based on its number of moles, or we can figure out the other way around. If we know pressure or volume, we can figure out number of moles and then do stoichiometry from there. So let's look at some examples. So our first example says a mixture contains 5 grams each of oxygen gas, nitrogen gas, and neon gas. Calculate the volume of the mixture at STP. So this is just an ideal gas law equation. So we're not going to end up doing any stoichiometry with this. The hint here is that there's no reaction. We're just looking for a value. So if we want to know the mixture and we want to know volume, we know that we can go from grams to moles. Because if we think about our ideal gas equation, we have pressure, volume, number of moles, our constant, and our temperature. Well, STP tells us our temperature and our pressure. We're trying to calculate volume, and we have some information that can tell us number of moles. So if we convert each of these individually to moles, so we're using the molar mass, so 5 grams of oxygen divided by 31.998 grams in 1 mole, 0.156 moles of O2. Keep going down the line, do that same conversion for each of them. Add them all up, our N total, or our total number of moles, gets us to 0.582 moles. That's the total number of moles of gas that we have in this container. From there, we're going to use our number and plug it into our ideal gas equation. So we have PV equals nRT. It's easiest if you isolate the variable you're solving for. So volume, or V, equals nRT divided by P. Then all you have to do is plug the numbers in. So our N is our 0.582 moles. That's that's the sum of all the moles of the gas. Our constant, 0.0821 liter atmospheres per Kelvin moles. STP is standard temperature and pressure. Standard temperature is 0 degrees Celsius or 273 Kelvin. And our pressure is 1 atmosphere because standard pressure is 1 atmosphere. Plug that all into your calculator, you get a number out, and you get 13 liters. So our 0.582 moles of gas, our mixture, at standard temperature and pressure occupies 13 liters of space. So here's one that actually involves stoichiometry. We have a reaction going on. So we have if 4.74 grams of calcium carbonate is heated, what volume of carbon dioxide would be produced at STP? So when you heat calcium carbonate, you get 2 products. So this is a solid, so that's what we're starting with. And we get our solid calcium oxide, and we get carbon dioxide as a gas. And our question asks, what volume of carbon dioxide? Now, if we have our ideal gas equation, remember PV equals nRT, if we're looking for volume, STP, so we have our pressure, we have our R, we have our T, we still need to find our N, and this is where the stoichiometry comes into play. So we have 4.74 grams of calcium carbonate. Before we can do any stoichiometry, we need to convert that to moles. 4.74 grams, and there are 101 grams in 1 mole of CaCO3, calcium carbonate. You calculate that, you get 0.0474 moles of calcium carbonate. What we need to know is moles of carbon dioxide. That's our gas. So N of CO2. That's a question mark. This is the stoichiometry part. We have a 1-to-1 ratio between our calcium carbonate and our carbon dioxide. So for every 1 calcium carbonate we use, we produce 1 carbon dioxide. So if we use 0.0474 moles of calcium carbonate, we're going to produce the same amount of carbon dioxide. So this is actually equal to the same thing, 0.0474 moles of CO2. At this point, if you don't need to do the whole BCA table, that's fine. If you can just tell me that it's a 1-to-1 ratio and do the calculations necessary, for this there are none because it's just multiplying by 1, that's fine. I don't need to see the whole BCA table at this point. So we know that our number of moles of calcium carbonate is 0.0474. So now our N is taken care of, and now we can solve for V, or for our volume. So again, we have our ideal gas equation, PV equals nRT. If we rearrange that, volume is equal to nRT divided by P. So volume is equal to 0.0474 moles. Now we're just plugging our numbers in. 0.0821. Standard, it was at STP, standard temperature is 273 Kelvin. Standard pressure is 1 atmosphere. When you plug all of this into your calculator, you should get a number out, and you should get 1.06 liters. So what this tells us is that if we were to heat calcium carbonate, we'd get calcium oxide left in our test tube. Say, for example, we were capturing all of the carbon dioxide produced, and our conditions were at STP, so we were at 0 degrees Celsius and 1 atmosphere. We would have produced 1.06 liters of gas. So same thing that we did with stoichiometry before, we can't measure moles. Remember, moles is just telling you how many particles there are, or how many molecules. What's useful for gases is not grams. We can't really measure grams of a gas very easily, but we can measure the volume of a gas fairly easily. And that's why we're concerned with that number.